We certainly know Earth's weather can be dramatic, but beyond our planet, storms also rage, and sometimes for centuries. Winds roar faster than sound, and rain falls as methane, or even diamonds. Today, we'll explore the science behind the weather on other worlds. When you boil it down, weather is all about energy transfer. On Earth, it's the sun that creates temperature differences, and they in turn drive winds to form clouds that can lead to rain. Other planets have similar principles, but with unique twists. Factors include atmospheric composition. What is the air made from? Gases like hydrogen, methane, or carbon dioxide can change the way the heat moves. Rotation speed of planets has an impact. A faster spin creates stronger jet streams. And then there's internal heat. Gas giants like Jupiter radiate or give out more heat than they receive from the sun, and that fuels colossal storms. Let's take a look at the different types of wild weather each of our neighbours in the solar system has to offer.
Oh, hey, just before we head off across the solar system, if you are enjoying this video, please do like it. Hit that thumbs up button. It's really good for us, really good for the algorithm. We put quite a lot of research and energy into making these videos, and we really want to spread the word, spread the love as far as we can. And if you haven't hit subscribe yet, then please do that. Subscribe to our channel. Also, it helps us to make more of these videos. Right, enough from me. Let's head away from Earth and see what the weather's doing on other planets.
First up, Mercury. Not the most scintillating place to start, as it has almost no atmosphere, so no clouds or winds really. Meteorologically, it is a bit dull. But it does have some brutal temperature swings, from plus 430 Celsius in the day to minus 180 Celsius at night. While in the UK, we would marvel at a 20-degree diurnal range. That's the difference between daytime high and nighttime low. If there were any Mercurians around here, they could be looking at over 600 degrees of a change in just one day. But then their days are a bit different, being over 1,400 hours long. If we're looking for something more juicy, well, Venus is the opposite of Mercury. Too much atmosphere here, a dense carbon dioxide sky, 90 times Earth's pressure with sulfuric acid clouds. Nice. Winds reach over 220 miles an hour here, and they have a runaway greenhouse effect, which makes it hotter than Mercury, despite being farther away from the sun. Temperatures on Venus can exceed 450 Celsius. The atmosphere is so thick that only about 3% of the sun's light can get through, so it's actually quite hard to tell the difference between night and day anyway. And the days on Venus are long, by the way, over 5,800 hours long. Now, the only other planet that we can get regular weather updates from is Mars, thanks to NASA's rovers. We know Mars is cold, with an average temperature around minus 65 Celsius, and it has a thin atmosphere at the surface, about 100 times less dense than ours on Earth. Because it has a tilt and a fairly eccentric elliptical orbit, Mars also experiences seasons. Like Earth, the different hemispheres point more or less towards the sun at different times of the Martian year. During the day, temperatures close to the equator can get up to 20 Celsius, but then at night, with only a very thin atmosphere unable to retain any warmth, the temperature can drop to minus 100 degrees Celsius or lower. Clouds can and do form on Mars. They're generally higher in the sky than on Earth and are made from ice crystals of water and carbon dioxide, or also dust. These clouds can also generate snow. That's actually been observed falling by one of NASA's rovers. Water ice snow will turn to a gas before it reaches the ground, but CO2 ice, or dry ice, can find its way to the surface. Another aspect of Martian weather that's actually been measured is lightning. In 2026, scientists revealed that the Mars rover Perseverance had detected electrical discharges named mini lightning that were picked up from audio and electromagnetic recordings made by the rover's SuperCam instrument. Mars has powerful winds and experiences the biggest dust storms in the solar system. These storms can cover the entire planet for weeks, powered by sunlight, heating the surface and lifting the fine dust. And Mars's vast, dusty desert-like surface can also experience smaller dust devils, twisting, a bit like tornadoes on Earth, and these have also been caught on camera. The red planet also has polar ice caps, made of a combination of water and CO2. The poles freeze in the winter, and then the frost at the poles sublimates or turns straight from a solid ice to gas in spring, and that creates pressure changes that drive strong winds, similar to Earth's seasonal shifts, but far more extreme. The thin atmosphere makes it very difficult to measure the winds on the Martian surface, but by monitoring accurately the movement of the dust devils I mentioned earlier, it is now known that the winds can reach close to 100 miles an hour. Heading further away from the sun and the planets change from rocky to gassy. But just because there isn't as much of a surface to stand on, as it were, to look at the weather, it doesn't mean there isn't any meteorology going on. In fact, you could argue that Jupiter's Great Red Spot is perhaps the best known bit of solar system weather away from Earth. It's a high-pressure storm, twice Earth's size, and it's been spinning for at least 350 years. Jupiter's banded clouds are driven by the rapid rotation and internal heat, and made at least in part of ammonia. Whilst Jupiter's atmosphere may be very different to Earth's, one thing the largest planet has in common with us is a magnetosphere, kind of like a magnetic protective bubble that sits around the planet. And it means it can also generate aurora, something which has been observed on Jupiter. And that is also true of the next planet along. Famous for its rings, Saturn has also been seen glowing from its aurora. Saturn's atmosphere is similar to Jupiter's, but being twice as far away from the Sun, it is significantly colder, with temperatures around minus 176 degrees Celsius. It also boasts the second strongest winds in the solar system, with speeds of around 1,100 miles an hour. Occasionally, violent white storms break through the cloud layers, each one being bigger than Earth. One of these was observed by the NASA ESA Hubble Space Telescope in 1994. Smaller storms also do occur and can appear as darker spots. Saturn, like Jupiter, generates heat from its interior, and that's what really drives its weather and its atmospheric circulation. The combination of this internal heat radiating out and its fast rotation, a Saturn day is only 10 hours long, creates circulations and high-speed winds in rivers, not dissimilar to our jet streams. And one such jet stream that operates around the pole is hexagonal in shape, with sides around 9,000 miles in length. So that's larger than the radius of the Earth. Another phenomenon is the Great White Spot, a massive periodic storm that seems to develop around every 30 Earth years. These storms are immense. They can grow to encase the entire planet, with the 2010 episode expanding to cover an area 8 times the surface area of Earth. The Great White Spot gets its name, obviously, from its bright white colour, thought to be caused by fresh ammonia ice crystals formed as warm gas plumes rise up through the upper atmosphere. Smaller cyclones and lightning storms are also quite common on Saturn. Powerful lightning bolts, up to 1,000 times stronger than those on Earth, have been observed by the spacecraft Cassini. Now, there is a place in the solar system that has similar weather to Earth. It has a cycle, like the water cycle. It has clouds that rain, and even rivers. I'm talking about Titan, Saturn's largest moon. And it's a bit too cold for humans, with an average temperature around minus 180 Celsius. Oh, and the clouds and the rain and the rivers, they're made from methane, not water. Methane, though, isn't the strangest thing to fall through atmospheres in the solar system, as we head further out and it gets even colder. Recent research suggests that extreme pressures and temperatures deep within Uranus and Neptune create conditions where carbon atoms crystallize into diamonds, forming a continuous diamond rain. Uranus is tilted at an impressive 98 degrees. It has seasons, but they're long, 21 Earth years, in fact. Now that is a long winter. Because of its tilt and duration of the seasons, parts of the planet can point almost directly towards or directly away from the sun for decades, creating large temperature variations over the planet, helping to drive the weather systems and create huge storms. The spacecraft Voyager 2 saw discrete clouds, a great dark spot and a small dark spot during its flyby back in 1986. And more recent observations reveal that Uranus exhibits dynamic clouds, including rapidly changing bright features. Uranus has a thick atmosphere made mostly of helium and hydrogen, but also some methane and traces of water and our old friend ammonia. Neptune also has a methane component to its composition, which is responsible for its blue colour and therefore its name from the Roman god of the sea. Its thick atmosphere is covered by constantly changing clouds that whip around the planet at high speed. In 1989, a large oval-shaped storm in Neptune's southern hemisphere, dubbed the Great Dark Spot, was large enough to contain the Earth. That storm has since disappeared, but new ones have appeared on different parts of the planet. Wind is the name of the game on Neptune. Wind speeds here have been measured at close to 1,200 miles an hour, making them the fastest in the solar system. Okay, let's move on to the upside-down world of the dwarf planet at the edge of our solar system, Pluto. Here we have snow-capped mountains, but it's a very different kind of snow. In our Earth world, or at least in the lower part of our atmosphere, the temperature drops the higher you go. You feel it as you climb up a tall mountain. But on Pluto, the opposite is true. It's actually warmer the higher up in the sky you go compared to at the surface. Yes, there is a temperature inversion on Pluto. The average atmospheric temperature at altitude can be tens of degrees higher than it is at the surface. And this is because the atmosphere is so thin on Pluto that it doesn't really warm the surface. And it's the methane in the air that traps the little heat that it gets from the sun. And the way the atmospheric dynamics work on Pluto, there are higher amounts of methane higher up in the sky. And that can create the snowy peaks on the mountains when there's simply not enough methane to form any frost or snow at lower levels, even though it is colder here. Maybe we should do a deep dive just on the weather in Pluto. From acidic clouds to supersonic winds, weather beyond Earth is a story of physics and on a grand scale. Understanding these systems helps us learn about our own climate and also the possibility for life elsewhere. Thanks for watching, and if you like this, you might want to come back closer to Earth by watching this video all about satellites. Make sure you like and subscribe for daily uploads.